Hi everyone, we're going to start chapter 7 now. We're going to start with exponential functions. We're going to talk about exponential growth and exponential decay, and that's a term that you've probably heard of quite a bit. What does that even mean? We live in a time of exponential growth. Exponential growth looks kind of like this. You have a slow increase, really gradual increase. And then it starts to pick up, and then all of a sudden, whoosh, it goes way up really fast. That's what exponential growth looks like. I was reminded about transportation, the kind of transportation that we live in now. I was being reminded about Daniel's time, some of Daniel's prophecy about people running to and fro in the earth. And in his day, the fastest anybody ever traveled was a horse. Well, Daniel was thousands of years ago. And that method of travel, that fastest mode of travel, did not change for thousands of years. For thousands of years until until the 1800s, when the steam engine was developed. And all of a sudden we could get trains where people were amazed. We could go 15 miles an hour. They were freaking out, panicked. They were going so fast, which sounds funny now, but yeah. And then cars. And whoa, until now, within 50 years, we had people going to the moon. This is exponential growth in just one area. That would be transportation. You can look at a similar idea about populations, the general population of the world kind of remaining steady until it reaches this point where it climbs really fast and then whoosh, exponentially really grows. Technology. You are in an era of technological growth where you can't even keep up. Think how I feel. When I was a kid, color television was it. That was it. Cassette tapes were new when I was a kid. We had 8-tracks. Look at where we are now, technology-wise. Exponential growth is what you want in your investments. You invest, $1 way, way back, and it kind of sits there for a while until, whoosh, here's exponential growth. That's what we're looking for in investments. So that makes looking at exponential functions fun because they have real applications to what we're doing in life. And we can also have exponential decays where things drop suddenly and then kind of level off. So they look reverse. They start high, come down, and then level off. An example of exponential decay then would be when I was young, there was a severe nuclear accident in Chernobyl, Russia, where involving a nuclear power plant, and it contaminated a huge region, lots of people, and the ground for a big radius around that plant. At that point, nobody dared go even near there. The radioactivity was so high. But the radioactivity drops pretty fast and then kind of slowly levels out after that. Now people are going back to that area. They're with much less protective clothing. Finally, it is the decay factor of that radioactivity has changed enough where it is much, much safer. So that would be an exponential decay. Here's the basic form of an exponential function looks like this. B is a constant. It is the growth rate or the decay rate of the exponential function. How much is it growing? Is it doubling? Is it tripling? Or is it halving? What's going on with this? That's the base. It's positive and it's not 1. Because a base of 1 will never change. It's 1 times 1, no matter what the exponent, it will always stay 1. So it is a positive number, not a 1, and this obviously can't be a 0 or we wouldn't have it. And then the x then, our domain, is the amount of time. How much time or how many periods has this happened? If it doubles every year, how many years have passed? If it doubles every week, maybe this exponent would represent week, but how many of those bases, how many times has that occurred? That's the exponent. This a term is basically what we started out with. So let's say we started out, well, we'll look at this and apply it to real life in a minute. Let's start by looking at what a graph looks like. What does this exponential growth look like? And we'll make our base 2. So this growth rate is 2. Whatever we have is doubling over however many periods, and that's going to be our domain. So I've selected x's from -3 to 3. This x is all real numbers, all the way to negative, all the way to positive. My bases are positive, but my domain is the all real numbers. So let's say I have this to the power of -3. So if I have 2 to the power of -3, that means 1 over 2 cubed, right? Or it means 1/8. So this is 1/8. Or if you put it in your calculator, you would get a decimal. To the power of -2 would be 1 over 2 squared, or 1/4. To the power of -1 would be 1/2. To the power of 0 would be 1. So anything to the power of 0 is always 1. 2 to the power of 1 is 2, 2 squared is 4, and 2 cubed is 8. Let's look and see what this looks like on a graph. I've plotted the points from my table, -3, 1/8, etc. And now I'm going to go ahead and connect them. This part goes like that and up like this. There is my exponential growth. That's just with a base of 2. I want you to notice what happens to this left side, and I want you to think logically as these negatives get bigger and bigger. What happens to my y's? They keep getting smaller and smaller and smaller and smaller, right? So this negative exponent keeps getting 1 over 2 cubed, 2 to the 4th, 2 to the 8th, and I keep getting smaller and smaller and smaller and smaller and smaller, but I never become negative, and I never become 0. It just gets infinitesimally, whatever that word is, smaller, really, really tiny. So this graph approaches 0 without ever touching it. So a line that a graph approaches without ever touching has a special name. We call that an asymptote. So y equals 0 is the asymptote that this graph approaches and approaches, go as far to the left as we want to go for all of eternity without ever touching it. It quite can reach 0. Then notice when x is 0, we are going to have a value of 1, and pretty much that doesn't change. And then it climbs up really steadily, really quickly from there. This is typical of an exponential graph. I'm going to draw a couple more graphs. Now I'm going to draw one with a base of 1/3. What is that going to do to my graph? So here is, I started my table, I set up my domain from -3 to 3. Now I'm going to plug them in. If this is to the power of -3, then that's going to invert this, isn't it? And that's going to become 27, because it's going to be 3 cubed over 1 cubed. And to the power of -2 would be 9, because it would be 3 squared over 1 squared. And to the power of -1 would be 3. To the power of 0 would be 1. This would be 1/3. This would be 1/9. And this would be 1/27. Let's go ahead and plot those points. Okay, here is my graph when the base is 1/3. Notice this one started big from the left and went down really quickly. Also a little steeper because of that 3 instead of the 2. And now still, y equals 0 is still my asymptote because it will not get 0, but it approaches 0 as my x's increase, where the other one was as my x's decreased, it approached 0. This is exponential decay. Now let's do one where our number in front is something other than 1. Now I have a 2 here. So I have 2 times a base of 3 to the power of x. Let's see what this looks like. Okay, now let me just go over how I filled out this table. If I made x to the negative 3, I'm going to do exponents first. 3 to the power of negative 3 is 1 over 27. Times 2 would be 2 27ths. Same thing here. To the power of negative 2 would be 1 over 9. Times 2 would be 2 ninths. To negative 1 would be 1/3. Times 2, 2/3, etc. To the power of 0 is 1. 2 times that is 2. To the power of 1 is 3. 2 times 3 is 6, etc. Notice how quickly it climbed up. By the time x is 3, we're up to 81. So what will this graph look like? So here it is. Basic shape is still the same. We still have y equals 0 as that asymptote. So our range is y is greater than 0. Our domain is still all real numbers. It shows exponential growth, but it does cross the y axis at a different point. Before, when this was 1, it just crossed at 1. Now it crossed at 2. So 0, 2 is my y-intercept. So that changed. Otherwise, it looks very much like the other ones did. So here's what we discovered by doing that. When we take this basic exponential function, this base determines if it's exponential growth or exponential decay, like we said before. If it's bigger than 1, it's growth. If it's less than 1, like when we had 1/3, then it is exponential decay. This determines our y-intercept. So 0, whatever this number is going to be where we cross the y-axis. Our asymptote was always y equals 0, and our range then was y is greater than 0, no matter what numbers these were. So that in general is what we can see with these exponential graphs. So now we're going to look at a couple of these functions and answer a couple of questions. Is this exponential growth or decay, and what is the y-intercept? So based on this, because my base is less than 1, this is exponential decay. What's my y-intercept? My y-intercept is always 0a, so my y-intercept would be 0, 12. That's how you would answer that with this equation. Here's another one. We're going to ask the same questions to this function. Y equals 0.25 times 2 to the power of x. My base is 2. So is this growth or decay? 2 is greater than 1, so this is exponential growth. What's my y-intercept? My y-intercept is 0, and this, my 0a, so it's 0, 0.25. That's my y-intercept. Let's answer the same questions with a word problem. Let's say you have $1,000 and you put them into a college savings account for 4 years at 5% interest. Would that be growth or decay? Well, you're adding 5% every year, so that is exponential growth. What's the y-intercept? The y-intercept is the amount that you put in at the beginning, so 0, 1,000. That the amount you had at the beginning is that y-intercept. Your y-intercept would be 1,000. Okay, that last question regarding money that you put into that college account, it reminds us that this is a really super helpful formula. This is a way to model and set up any kind of exponential function of either growth or decay. You can use this. So put this in your notes. This is what this means. The amount that you have in terms of the time is the initial amount times, and this is 1 plus the rate. If it's a growth rate, it will be positive, and if it's a decay rate, it would be negative. And then the t represents the number of fixed time periods. Most of the time it's years, but it could be something else. So the tricky part about this is this rate. If it's growth rate, it's positive, we're adding it to 1. If it's a decay rate, we're subtracting it from 1. so that our decay rate would end up then being less than 1. So this rate is either positive or negative, depending on if it's growth or a decay. So let's apply this to a few real situations. So let's say you're given $1,000 or you earn $1,000 and you put it into an account after 6th grade to save for college. And this account that you put it in earns 5%. So what I want to know is how much money will be in that account after 6 years when you graduated from high school now and you're ready to use it. So this is what you're going to use to answer that question. That's why you really want it in your notes. So the amount, the A of 6 is what we're looking for. The amount after 6 years is our initial amount, which was 1,000. So for this is going to be 1,000. And then it's 1 plus our growth rate. It earned 5%. Change that to a decimal. So that's 0.05. And then our time period is 6 to the power of 6. So what we have is 1,000 times 1.05 raised to the power of 6. And in your calculator, you do, depending on, do exponents first. 1.05 raised to the power of 6. Multiply that times 1,000, and then you will get your answer. And you should have gotten about $1,340.10. So you got $340 that you didn't do a thing to earn. It just was added. It just grew exponentially. Okay, you may get a problem like this where you have to solve for t. So let's say you have that $1,000 and you put it in an account that earns 5%. The question is, how many years will it take for you to have $1,500? That's of course assuming you make no additional deposits or withdrawals. You just let it sit there. So what you would do to do this is you could put, this is 1,000 and this is 1.05, and then just with your calculator, just try different years. We already know it took 6 years to get to 1,340, so it's going to be more than 6. Until you can use a table in your calculator or whatever, but you just kind of keep working until you find the answer that you're looking for. There's got to be a way to solve for x, and there will be. I'll show you that in the future. If you work through this, you will find that you won't have this much money until after 9 years. It'll take you a little more than 9 years to get up to $1,500. All right, there's a problem in your text on how to, that regards a particular species of cat, I think an Iberian lynx or something like that. And they were monitoring this population of this lynx, and in 03 it was 150, and in 04 it was 120. So the question was, based on this data, how many lynx would you expect there to be in 2014? So in order to do this, you have to find the rate of decay. Obviously, this is a decay rate because it's going down. And so we need to find that rate, and I'll remind you how to do that in case you're not sure. And then we need to set up an equation for how to solve this. So to find the decay rate is the amount of change over the original amount. That's what you do. So the amount that it changed was 30. It went down 30, so 150 minus 120, that's 30. And 30 divided by the original amount, that gives us our rate of change. This is 1/5 or 0.2 is our rate of change, and it went down. So that is a negative because this was a negative 30, right? So it's a decay rate of negative, or decay, it went down 20%, so it's negative 0.2. That's our R for our equation that we set up before. So here's how we would set up our equation. We would have y equals, and remember we have a, b to the power of x, right? Our a is the initial amount. Our initial population was 150, so that number is 150. But now we need to find our B, or our rate. And if you remember, it was 1 plus R. In this case, our R is negative 0.2. So 1 plus negative 0.2, or 1 minus 0.2, which is 0.8. Do you see this is how a decay factor or a decay rate would work? We are losing 20% each time, so we're left with 80%. It's 1 minus our decay rate, and that gives us our new base, 0.8. And what we're trying to figure out now, what would this be right here? So how many years are there from 03 to 14? And of course, 14 minus 3 is 11. So there's our equation to see what we would expect the population to be in 2014. So 0.8 to the power of 11, multiply that times 150, and you get your answer. According to this model, you're only going to have about 13 of those cats left. Okay, for your lesson check for this section, I would like you to tell me that if this trend continues, what would you expect the population of this Iberian lynx to be in the year 2020, which is the year we are right now? So apply this whole scenario, only now answer the question for 2020. That's your lesson check. And that's an introduction into exponential functions. And so I'll see you guys next time.